Listen to part of a lecture in biology class. You've been reading about animal behavior. Today we'll discuss one of the most astonishing behaviors in the animal world, dancing bees. Did you know that bees can dance? Well, neither did scientists until the 1960s. That's when a German scientist named Karl von Fritsch noticed something truly remarkable. As he was observing honeybees, he noticed that some of the bees, which he called scout bees, flew out of the hive to look for food. When a scout found a site where there was food, it flew back to the beehive and started dancing. This dance somehow told the other honeybees where the food was, because after the dance, some of the bees flew from the hive straight to the site of the food. Von Fritsch called the bees that collect the food forager bees. He thought the scout bees' dance told the forager bees three things. First, the smell of the food it had found. Second, which direction to fly to reach the food. And third, the distance of the food site from the beehive. Von Fritsch won the 1973 Nobel Prize for this discovery, but many scientists were skeptical of his theory. They didn't believe it was the dance that led the forager bees to food. Instead, they thought it might be, the smell of the food in the dancing bee, or maybe that they just followed the scout back to the food site. Well, very recently, some British scientists used a new type of radar to prove that von Fritsch's theory was indeed correct. It is the dance that communicates this information to other bees. British researchers found that the scout bees perform two types of dances. If the food is near the hive, say, about 50 or 60 meters away, the scout flies in a round pattern, like a circle. This tells the location, but not the direction of the food site. If the site is farther away, the scout does what's called a waggle dance. It flies in a pattern of ovals and vertical lines. The speed of the waggle dance tells other bees how far away the food site is. The slower the dance, the farther away the food. If the scout flies in a vertical line up the side of the beehive, it's telling the foragers to fly directly towards the sun. If the scout flies vertically down the hive, it's saying, fly away from the sun. Up is toward, down is away. If the scout flies at an angle to the hive, it's telling the foragers to fly neither toward nor away from the sun, but in between. The bees have a special internal mechanism to know which angle they should fly based on the sun, the hive, and the food site. They can also measure the distance they fly by recording the motion of things they see as they fly past. Now, one problem with von Fritsch's theory had been this. It seems to take the forager bees a long time to reach the food site. That's why scientists thought that perhaps it wasn't the waggle dance that led them there. For many years, scientists couldn't follow the foragers after they left the hive, because they didn't have the technology. Just a few years ago, though, the British scientists solved this problem using a new type of radar. They were able to attach a small radio transmitter to forager bees. I don't know how, but they did. This enabled them to follow the forager bees' flight after they left the hive. The radar showed that foragers do, in fact, fly straight to the area of the food site. They don't follow the scout bee back to the site because the scout goes into the hive after it finishes dancing. Well then, if the waggle dance does lead the foragers directly to the food site, why does it take so long for them to find the actual food? The answer is that the waggle dance leads the foragers only to the general area of the food. It doesn't tell them the exact location of the flowers or plants that have the food. So the foragers have to spend a while flying around the area before they find the exact location of what they're looking for. Listen to part of a lecture in social science class. Today we're going to begin with a short quiz. No, you don't need pencil and paper, just listen. It's only one question. Ready? Okay. What do blogs, Pokemon, tattoos, Cabbage Patch Kids, pet rocks, and hula hoops have in common? Anybody?
They're all stupid.
I know, Professor Morgan. They're all fads.
Correct. Now here's another question. How did you know that? In other words, what are the characteristics of a fad, and what's the difference between a fad and a trend? These are the questions we're going to consider together this afternoon. Well, the main difference, I think, between a fad and a trend concerns time. A fad is something that seems to appear suddenly. It quickly becomes enormously popular, then disappears just as suddenly as it came. A trend also appears rather suddenly, and it also becomes very popular, but it doesn't disappear. A trend can have a long-term influence on its particular market. Fads and trends often resemble each other at first glance, but a fad usually has a definite beginning and end. Pokemon might be a fad, but the idea of fancy playing cards for children might be a trend, for example. Another difference is that fads usually stay within one industry. Trends can cross over into many industries. The hula hoop, for instance, has been called the greatest fad of all time. 25 million. In the late 1950s, 25 million hula hoops were sold in just 4 months. But a year later, sales had virtually stopped. The hula hoop was a toy. It was fun to play with, but that's about all. Now consider cell phones. They were designed to be portable telephones, but they crossed over into the worlds of fashion, wireless communication, and now even photography. People buy cell phones that match the latest clothes fashions. They use cell phones for wireless internet access. They take photos with them. Cell phones have become a trend. Here's the third difference between fads and trends: how well industries accept them. Fads are often promoted by smaller companies. They need the quick money that fads provide. Large companies don't accept fads right away. They can't afford to be wrong. If a company is known as a trendsetter and it promotes a fad, its reputation will be damaged. Large companies buy products in huge numbers. They don't want unsold products sitting on their shelves. So they wait to see if a fad becomes a trend. Then they will accept it in their stores. Now, yes.
How long does a fad have to last before it becomes a trend? I mean, there are all these energy drinks now. There used to be only a couple, but now there's like 100. Are they still a fad? Exercise is a trend, so wouldn't energy drinks be part of the exercise trend?
That's an excellent question. When exactly does a fad become a trend? You know, there are some people who are paid a lot of money to answer that question. If they get it right, companies become rich and famous. If they get it wrong, companies go bankrupt and careers get ruined. The short answer is, nobody knows. Distinguishing between fads and trends is an art, not a science. If it were easy, there would be a lot more rich people in the world. Yes, in the back.
Yeah, can't people get rich from fads too? You said they sold 25 million hula hoops in 4 months. Someone must have made big money off that.
Yes, they did. Toy companies made $45 million off of hula hoops by the time the fad ended. And maybe some of you have heard of pet rocks in the 1970s. A man bought a rock for a penny, put it in a gift box, and marketed it as a pet. He became an instant millionaire. But the trouble with fads is, no one can predict them. This man had no idea that so many people would buy rocks as pets. He started it as kind of a joke. The Pokemon creators had no clue their cards would become instantly popular all over the world. That's the thing. Fads are mysterious to both their creators and to the public. Listen to part of a lecture from a marine biology class. You've been reading this month about food chains and food webs. Today we'll discuss these in relation to seafood. How many of you like seafood? Most of you. So do I. In fact, I'm on a seafood diet. I see food, I eat it. Get it? Okay. But seriously, folks, today we're going to talk about trophic relationships in marine food chains and webs. Who can remind us what a trophic relationship is? Yes, Miss Lee.
It's what an organism eats and the things that eat that organism.
Very good. Trophic relationships describe the relationship between producers and consumers, so they help us diagram food chains and food webs. Now, in marine ecosystems, like other ecosystems, food is needed for matter, growth and reproduction, and for energy, metabolic processes within the body. Also, like other ecosystems, marine ecosystems have producers, consumers, and decomposers. The primary producers are autotrophic plankton. Autotrophic means these plankton can synthesize their own food. Autotrophs are consumed by heterotroph organisms. Hetero means other. So in this case, heterotrophic means organisms that can't synthesize their own food. They must rely on autotrophs for food energy. The primary consumers in marine food chains are the plant eaters, herbivores, and the secondary consumers are both the meat eaters, carnivores, and predators that eat both meat and plants, omnivores. The decomposers are heterotrophic bacteria, which get energy from body wastes and dead tissue, thus cycling it back to the producers. A simple marine food chain then might look like this. The top predator, trophic level number 4, is a herring. Herring fish eat level 3, carnivorous zooplankton. The carnivorous zooplankton eat trophic level 2, herbivorous zooplankton, and herbivorous zooplankton eat level number 1. Photoplankton, which is a type of autotroph. In marine food chains, energy transfer is not very efficient. Photoplankton utilize only about 1% of the energy available from the sun. Between 70 and 90% of the energy made by producers or eaten by heterotrophs is used in their bodies or expelled as waste. This leaves only 10 to 30% that is retained in the body's biomass and available for consumers at the next highest trophic level. Thus, the biomass at each trophic level is controlled by the efficiency of the energy transfer. At the lowest trophic level, animals will generally have high biomass, and there will be lots of small producers. At the highest trophic level, animals will generally have low biomass, and there will be only a few large animals. Now, let's expand our simple food chain into a food web. In this web, a herring is no longer a trophic 4 predator. There is a bigger fish, a tuna, that eats the herring. But there's even a bigger animal that eats the tuna, and that is...
Us.
Yes, and there's something else from the seas that will even eat us.
Sharks.
Correct. A food web is more complex than a food chain. And then there are gigantic animals like whale sharks and baleen whales that are herbivores and only eat plankton. But let's focus for a few moments on us. What are the implications of trophic levels for the fish we eat? Well, looking at the fish harvest worldwide, 88% of the fish we catch are fish with fins. 8% are shellfish, and 4% are crustaceans. Fish caught in the open ocean, such as tuna, are high-level predators on an inefficient food chain. Fish caught in coastal waters, such as cod, herring, and haddock, are at the top end of shorter, more efficient food chains. This is because there's a high level of photoplankton, so consumers expend less energy catching food. These fish, then, provide more energy and better nutrition for us. In upswelling areas off the west coasts of America and Africa, the fish are even healthier. Here they are small, very efficient food chains, and the fish are small, fast-growing, eat lots of phytoplankton, and travel in dense schools. Two examples of such fish are anchovies and sardines.